last time we did hypothesis tests for means problems. Yes?
If we have time at the end of class, or maybe before, whenever you think is appropriate, on the online homework, there was a question that I did like multiple times, and I kept getting the same thing wrong, and I couldn't figure out how to get it right. It gave you a big table of information, you know, patient. It was a crossover, and then A and B, and
Yep.
then you had to do the
I
differences.
know the problem.
And I did the differences, and I'm pretty sure I got all the differences right, and then when I went to go calculate the statistic, I kept getting it wrong every single time. And I don't know what I was doing wrong there. I mean, I was putting it into L1 and doing all that stuff, but
That's what I would tell you to do.
I know, I
So,
don't know what I was doing
Yeah.
wrong.
Mary Ann, did you have
I have the
comments
same
about that?
problem with that
Yeah.
question, and it's a computer program, and I noticed that throughout the semester, there's a couple times the computer program has been screwy, and you just have to do it, I had to do it like 4 times until I finally got it
You
right.
know,
I
it's
was
the whole
doing the
question over
problem,
and over and over
and it's like the world's longest
because you have
problem.
to input everything. That's what it's so horrible.
Yeah, so probably what happens, there's probably a bug in their system where
Yeah.
it's somebody entered the correct answer incorrectly. So you say do a similar exercise, you'll get a new version,
Yeah.
and then it might work. But if you keep trying to work the same one,
No, I mean, I did the similar exercise, and then I have to input all the new information and that stuff, but the T-statistics was completely different from the one that I was getting out of my calculator, and I don't know how. What was your problem with it?
I don't remember which one of the, like, I think it was the T that was wrong,
Yeah.
the Z was right, so I'm like, I knew I was doing the problem right.
Exactly, that's what
And
my
I kept
problem
doing
was.
similar exercises, and I would do it the same way, and I finally got it.
Yeah, I mean, I quit after like 3 times, and I just
I
accepted the
think I
one
do
little
it like
tiny wrong
4.
part of the whole question.
yeah, when that
But
happens
once
to you,
they give you the T-statistic, then I can do the rest of it.
yeah.
But the p-value I got was right, but the test.
Well,
statistic
you know,
wasn't.
when that happens to you, ask my instructor,
Okay.
and say, I don't think this one is correct, there's a bug or
Okay, well, I'll
something.
try to do it again
And
today,
then I'll
and
forward that to them, and they can fix the problem. Otherwise, I just say, you know, some of the versions of this we seem to be having trouble with, and then they have trouble
Okay.
identifying it, but,
I'll
so.
try to do it again when I get home and then send it to you if it don't do it wrong again.
Okay.
I had a similar problem, but it was one of the questions that didn't end the sentence. It was is, and it was supposed to be like not or is true, but it didn't show.
So there was like typos in the way that they had, like,
They wouldn't finish the sentence. The one it
yeah,
was the
so you
one
couldn't
part that
see
you
what
needed.
the right answer, yeah. I remember that one.
I didn't have that question.
And send me an email with a link to that one if you can.
I
and
redid it and it showed it, and I don't know why the first
Just-
time I did
yeah.
it didn't show it.
It sounds like they have some bugs in their system. If that happens to you and you get penalized points-wise,
Yeah.
just email me and I'll give you the points back, even if I can't get them to fix it.
Okay,
You know what I mean?
I'll try to work it when I get home and send it, but it was just, after so many times, I just accepted that. So I got 4.88 out of 5 possible on the question, and I was like, that's okay.
Yep.
When's our test?
Test is Monday, the 22nd, which is the last day of class before Thanksgiving break. And that way you can go on your break and have your turkey and everything and not have to worry about studying for a test. So, and that will cover up through section 10.1, which is an odd place to break for a test, but I wanted the test to be the last day before the break, so I went one extra lecture just to put it there rather than the Friday before. Because if I gave a test on Friday, guess who'd show up Monday? Nobody. Right? So, we're not going to do that.
I chill it.
Unless you brought like treats or something.
Yeah. Yeah, if I bribed you, you'd come to class. Okay, today is section 9.4, which is the different kinds of errors that you can make in the decisions from hypothesis tests. So errors in decisions. And the best way to think about this is like with a little 2x2 table. When you do a hypothesis test, when you get to step number 5, you make a decision or a conclusion. You say, I believe that this works, or I believe it doesn't work, or there's not enough evidence to say that it doesn't work. So I'm going to put that in terms of rejecting the null or failing to reject the null, then unbeknownst to the researcher, there is some population truth, right? And that truth is either that the null is true or the alternative is true, which is the same thing as saying the null is false. Now you don't get to know this, which is why you have to do hypothesis tests. You have to try to make inference about whether or not the null is true or whether or not the alternative is true. But God knows which is true, right? So from that perspective, here are the four possibilities. If you're in the case where the null hypothesis is true and you reject it, then you just made a mistake. Right? That's an error in your conclusion. That's called a type 1 error. Now somewhere else in this table is another type of error, which you might guess we'll call type 2. Where's the other error?
Fail to reject it when the alternative is actually true.
If you fail to reject the null, but the alternative is true, or in other words, the null is false, but you fail to reject it, then that's an error. And that's the type 2 error. A type 1 error we refer to as a false positive. And a type 2 error we refer to as a false negative. And the word positive and negative kind of comes from the perspective of if you're trying, usually when you do an experiment and you're testing a hypothesis, as a researcher, you hope to reject the null. The null means you didn't find anything. You don't have strong enough evidence to make your conclusion that you want to make. So you're hoping to reject the null. So if you do reject the null, we call that a positive study. Hey, I had a positive study. I showed that my drug's better than placebo, or whatever. If that's an error, then that's a false positive. A negative study is one that fails to find a difference, fails to prove what you hope to prove. So we say, oh, I had a negative study. If that's an error, we call it a false negative. The other two cells, you made the correct decision. Okay? So we hope that most of the time when we do an experiment and we do a hypothesis test, that we would make the correct decision from it. So how do you know whether you made the correct decision or not?
But you don't know.
Trick question. You don't know. You have no way to know. Just like the confidence intervals, we're 95% confident that this interval contains the true value. How do I know if it does or not? I don't. I'm only 95% confident that it does. And you never get to know the truth. So you never know whether you made an error or not. But what you can do is you can control the probability of making an error. So let's talk about probabilities of these errors. The probability of a type 1 error well, let's write down what that means. If you make a type 1 error, then that's saying that the null was actually true and you rejected it. So that probability is the probability that you reject the null given, so this is the conditional probability, given that the null is true. Okay? Now, let's think about this from one of the example problems that we did. Remember the dogs being able to smell cancer? Remember that example? And if I remember right, there were 5. The dog was presented with 5 little vials of, I think it was breath, right? So I don't know how they save your breath, but they somehow do that. They put the 5 vials of breath there, and the dog's supposed to pick which one smells like cancer, right? And the dog got it right 81 out of 83 times. Remember that? Now, it's possible that that could happen by random chance, that the dog cannot smell cancer. In other words, the null is true. The dog cannot smell cancer and just happened to sit by the right one 81 out of 83 times. By the way, how likely, what would that probability be? What do we call that probability? If I compute the probability of getting 81 out of 3 correct just by random chance when the null is true, what's that called? The p-value. That's what a p-value is, right? And if you remember right, the p-value was like something times 10 to the negative 70th power. It had 69 zeros, right? So it's saying, well, it's possible that the dog was just randomly sitting by these things and got it right 81 times, but it ain't very likely. So the probability that the dog rejects the null hypothesis by getting so many of them right, when in fact the null is true, that p-value is computed from the sampling distribution of p hat. Now the p hat that we observed was 81 out of 83. Where would this distribution be centered? It's not centered at p hat. It's centered at p. And what are we hypothesizing p is? Well, what was the null hypothesis for this problem? If they have 5 things to choose from, what's the probability that they guess correctly? 0.20, which is 1 out of 5, right? So the p equal 0.20 was the null hypothesis. So this is computed conditioning on the null being true. So what we're saying is if the null is true, then this thing is centered at 0.20. And then you compute this. Somebody do this on your calculator. What's 81 divided by 83? 0.9755? 59? And where does that fall? Relation to the center of this distribution. It's over here. That's about how many standard errors it is. Remember, it's 17.7 standard errors. And so 1 standard error would be halfway down the hill. So 2 standard errors is there. 3, 4, 5, 6, 7, 8, 9. Oh wait, I guess I'd be out in the hallway to get to 17.
Did it give you the standard error?
No, it didn't give me the standard error, but I could compute it.
We did that last time.
I don't know if we did or not. What is the standard error p hat? If the null is true. Remember how to compute standard error of a proportion?
No.
Yeah, you do. It's a big old square root. And then what's under that square root?
P hat minus 1.
Okay.
P hat over.
Only I'm assuming the null is true, so I don't have to use p hat.
Oh.
I use p0. So it's 0.2, 1 minus 0.2, divided by the sample size, which was 83.
Oh.
Remember that? So I don't know what that number is, but Delaney does.
.044.
0.044. Okay? So one standard error takes me to 0.24, another one takes me to 0.28, and so on. By the time I get to 0.97, I'm 17 point something standard errors out there. Okay? So I'm gonna bring that in here and we'll just put it right there. It's out in the tail, and it's a lot further out in the tail than that, but that's where I'm gonna put it. Shade for me the p-value. Where would the p-value go? Remember, p-value is a probability.
Out there.
Okay? It's that region, right? Now again, that's not far enough out, but because what is the p-value again?
The distance further or at your observation.
Okay, not the distance, but the probability of being that distance, right? So it's p, and p-value stands for probability. So it's the probability of getting the data you observed, or even further from the null, if the null is true. So the if the null is true part is what centers this thing at 0.20. Now we don't know if that's the right place or not. We're hypothesizing that. Okay. So now back to this question. What's the probability you reject the null by random chance? That's what this says. If the null is true, it's saying then it's random chance. The dog's just randomly guessing. What's the probability you reject? Well, where are you going to reject? This p-hat definitely we're going to reject, but there are other p-hats I would also reject for. In fact, I wouldn't have to go 17.7 standard errors in order to reject. How far would I have to go before I start saying, oh, that's enough evidence? If my p-value gets to where? To the alpha level, right? So, and that's going to be right around 2 standard errors. Probably 1.96 standard errors, right? If I'm doing a one-tailed test, it'd be 1.645 standard errors, because then I'd have all 0.05 up here. So I won't put a number with it, but we'll say that region. And let me use a different color, although the only different color I have is purple. And if you're like me, you can't really tell the difference between purple and blue. People get confused about the difference between alpha and the p-value. The p-value is here. The alpha level
Where it meets 0.05.
is all the way from here to infinity. That's alpha. The p-value is from here out to infinity.
So how do you know where to put that line at?
Yeah.
Which line?
The line you designated where alpha.
You tell me what alpha you want.
Okay.
You want 0.05? Then I move it so that that area is 0.05. And that cutoff, we don't worry about it in this class, but this is, you click on the help me solve this button, and they'll say, oh, if alpha is 0.05, look up the critical value for your test statistic. So they would draw the same distribution but centered at 0 for the standard normal distribution, and you go out to 1.645 instead of 1.645 standard errors.
Why would you do 1.645?
Because that gives me 0.05 in the tail.
Oh, okay. How do you know that? You just knew?
Yeah, don't you have it memorized?
No.
If you do inverse norm on your calculator, inverse norm of 0.95, you'll get 1.645, because that leaves me alpha equal 0.05 in the tail. So when the p-hat gets far enough out, like suppose I had a p-hat right there, then my p-value, again, is the area past p-hat. Is that area going to be bigger than alpha? Yeah. So I would fail to reject the null. But as my p-hat moves further away from the null, pretty soon it goes past this cutoff, which means my p-value goes below the alpha, and I reject. So here's a p-hat out there I'm going to reject, right? So what's the probability that I reject? Well, what percentage of p-hats would be out in that region?
Over 2 standard deviation.
And what percent is that?
97.5 minus whatever left.
Okay. See, you're reluctant. What I'm after is alpha. That's the probability. The probability that p-hat falls out there is whatever that shaded region is. So this is what we call the rejection region. And you have an alpha % chance of falling in the rejection region when the null is true. So this was an awful long-winded way to say that this probability is alpha. So how do you know if you made a mistake or not when you make a conclusion? You don't. But you can control the probability of making a type 1 error by setting your alpha level. If you want to set it at 0.05, then you're saying, I'm willing to accept that I have a 5% chance of making a type 1 error. 5 out of every 100 dogs will get lucky enough, if the null's really true, will get lucky enough to make it look like they can detect cancer when in fact they can't. That's what type 1 error means. That probability is alpha. Okay. Now what about probability of a type 2 error? That one we're going to call beta. So this is called the alpha level or alpha error for type 1. The beta error is the probability of a type 2 error. We will not in this class learn how to compute this beta error, but I will draw a picture of it. Okay? This is section 9.6 to compute it, and we're going to skip that section. But how would I compute that probability? Well, let's put it in this form again. This is the probability that you fail to reject given that the alternative is true. Right? Now again, let me try to use this black marker which doesn't have much ink in it. But here's my rejection region, and that's not going to move. This is a number line for p hats, which goes from 0 up to 1 out there somewhere. Right? If I fail to reject, that means I got a p hat that's on this side of that black line. Right? But if I want to compute the probability of being on that side of that black line, I have to do it under the condition that the alternative is true. This curve is drawn under the assumption that the null is true. But if the alternative is true, it won't be centered at 0.20. It'll be centered somewhere else. So where would it be centered?
Not 0.20.
At not point. Okay, how do I draw that? And that is exactly the problem. This is hard to compute. This is easy to compute. This is hard to compute because I don't know what p is. You tell me the alternative is true, and all I know is, well, that means it's not 0.2. But you didn't tell me what it is. You tell me what it is, and then I can draw a distribution. So suppose you tell me, well, the true proportion is 0.5. So now I come over here to 0.5. Say 0.5 is right there, and I draw a new distribution. That's at 0.5. Now I can compute the area of not being in the rejection region, failing to reject. That's going to be my beta. But you can only compute the beta when you're given some specific number for the alternative. Okay? So like I say, we're going to skip that. We're not going to actually go through those kind of calculations. But if this is beta, then what would 1 minus beta be? You should recognize 1 minus a probability as being something. What's 1 minus beta? No, it's not alpha.
Complement.
The complement, right? If you take 1 minus the probability of something, then you just found the probability that it does not happen. What is beta? The probability of? What?
It happening?
What's it? What does it say right here?
Oh,
Probability of a type 2 error. That's beta. So 1 minus beta is the probability that you don't make a type 2 error. Right? So that's the probability of rejecting the null given the null is false. Right? And that's called the power of the study. So you may hear people talk about, I did a power calculation. And as a statistician, I do a lot of power calculations, and they are closely linked to sample size calculations. And I'll demonstrate that in just a second. The power of a study is the probability that you get a positive result if you should get a positive result. So if the drug does what we think it does, then the power is the probability that my study demonstrates that. Or if the dog really can smell cancer, what's the probability that this study will show that the dog can smell cancer? So I make the right decision. That's called the power of the study. Okay? So let's talk about power and type 2 error from the perspective of a confidence interval, because that's easier than I think these pictures with p-values and shaded tails. And most of you look at those kind of pictures and you go, I have no idea what that says, right? But you understand confidence intervals usually a little bit better. Suppose I ran my study, not the same study they did, but I run some study with the dogs and I have them smell cancer, right? And I get a p-hat of 0.5 instead of 0.97. And when I put a confidence interval for the true proportion based on that, I center it at 0.5, and it goes from 0.15 up to, let's see, how far is that? That's 3.5, so up to 0.85. Is that centered at 0.5? Check my math. Confidence intervals are always centered at the point estimate, so, right? Would this confidence interval allow me to reject the null hypothesis? Here's my null hypothesis. No. So your conclusion is fail to reject. Does that mean the null is true? No. Do you see why we can never say, I accept the null as being true? You can never say that. All you can say is, well, I don't have enough evidence to say it's false. So I fail to reject. This gives me the set of all plausible values. And point 2 is plausible. The null hypothesis is plausible from this study. Now, notice how wide that confidence interval is? It's not very useful, is it? Suppose that the true proportion, unbeknownst to us, because we can't ever know the true p, but suppose it really is 0.5, and that my particular study did it exactly right. If I took, how would I shrink my interval down?
Become less confident.
Okay, I could become less confident, but if I want to stay the same amount of confidence, how do I make the interval narrow?
Larger sample size?
Take a bigger sample. That affects your margin of error, right? Makes it smaller. So if I take a bigger sample, I get stronger evidence. And suppose I took a bigger sample and I'm still centered at 0.5, but I go to, I get an interval from 0.3 to 0.7. Does that interval allow me to reject the null hypothesis? Yeah, now it does. For the same p-hat. So for this one, I failed to reject. Was that an error in my conclusion? Remember, I'm pretending I know what the truth is. Is that an error? if I fail to reject? Is the null true or false?
Did you say it was true or false? No, I don't remember.
I said, here's the value of P,
Okay.
right? So we get to pretend we're God and we know that the true value is 0.5.
Okay.
Is the null true? No, it's false. So this one failed to reject the null hypothesis. So is that an error?
Yes.
Yeah. And what kind of error?
Type 2.
Type 2 error. Now I take a bigger sample, I'm still centered at the same place, and it rejects the null hypothesis. Is that a correct decision or is that an error? It's a correct decision, because we know that null is false, right? So the point I'm trying to make is that the beta error, and therefore the power, are mainly functions of the sample size. If you got a small sample, you have a high probability of making a type 2 error, of not being able to say there's a difference. You take a big sample, you get nice tight confidence intervals, and you have a much higher probability of declaring the null to be false. Now, sometimes people misinterpret what I just said and saying, well, if you take a big enough sample, you'll always eventually declare the null hypothesis as false. Well, what if the null is actually true? What if it's really 0.2? But I take a big enough sample and I can shrink this thing down. How come I don't eventually make a type 1 error just by taking a bigger and bigger and bigger sample?
If it's true, it's gonna match your proportion.
Okay, what's going to match? You're absolutely right.
The interval will just.
It
be
won't
closer
center
together.
into 0.5, will it? It'll center in to the truth. So this p hat is going to get closer and closer to the true value. So as you take a bigger and bigger sample, remember we showed that with sampling distribution, that the sampling distribution for p hat centers at the true value. So if you take a big enough sample, you're forcing your p hat to get real close to 0.2. So the interval then still contains 0.2. So no matter how skinny you make the interval, it's still going to have 0.2 in it. You're still going to fail to reject the null hypothesis. So taking bigger samples does not increase your type 1 error rate. It decreases your type 2 error rate. Okay? Whew. It's kind of confusing stuff. So let's practice. What I'm going to do, I'm going to go through some of the homework problems at the end of the section. And for those of you that didn't bring a book, I'm going to pull it up on the screen using the e-book. But you can go ahead and get your books out if you have them and turn to the end of section 9.4. Oh, I forgot to turn on the projector. Did you hear the fan come on?
Yeah.
Is it running? It'll have to warm up for a little bit, but that'll give me a chance to get the page pulled up here. Okay, the first question is the one about the dogs smelling cancer. And unfortunately, this is as big as I can make it. So if you're at the back, if you had trouble reading that, then you'll have to rely on your book. It says, Dr. Dog, in the experiment that we talked about before, now here they put p equal 1/7, and I said it was 1/5, and I'm not sure if this is a typo or if I had read the example wrong before, but anyway, that's not really that important for what they're going to ask us to do. it says we got a p-value of essentially 0. For a significance level of 0.05, what decision would you make if the p-value is 0?
We reject the null.
You would reject the null. Now, what is that? What does that mean? My mom doesn't know what that means. Talk about dogs and talk about being able to smell cancer.
We have sufficient evidence to claim that the dogs are able to smell cancer patients.
Okay, that's perfectly fine. We have sufficient evidence to say that the dogs are able to detect cancer. Right? So that's our conclusion. So that's the decision we make. We reject the null and think the dogs can do it. If that happened to be an error, so this is part B. If you made an error in part A, what type of error was it? Is it a type 1 error or a type 2 error?
We reject the null.
Since we rejected the null, if that was wrong, then the null must have been true. So what kind of error is that? That's a type 1 error. Okay? So that would have had to have been a type 1 error because we rejected the null. Then it says explain what the error means in the context of the doctor dog experiment. Well, we kind of already said that. It means that we think the dog can detect cancer when in fact they can't. That's a type 1 error. Saying the dog can do it when in fact the dog can't. Right? Let me find another one that asks something a little bit different. Well, here's one. 944. This is one. This is an example I did not talk about in class, but it's in the text. In example 3, we were testing the null hypothesis that P was equal to 1/3. And that's whether or not an astrologer, you know what an astrologer is? It's a person that uses the zodiac signs to make predictions and stuff like that. Well, what they're saying is astrologers could predict the correct personality chart out of 3 possible ones for a given horoscope. Right? So you tell them what your horoscope is, and she can predict what your personality type is. Right? Out of 3 personality types. In the words of that example, what would be a type 1 error? What would a type 1 error be?
That you made the conclusion that she could predict when in fact she couldn't.
Right, that's right. You make, it's kind of interesting, people use he and she. It's kind of an aside. You said she. Why did you say she?
Because you said she.
Oh, did I?
I'm pretty sure.
Well, see, I'm guilty of it. You have this stereotype that
That's the fortune teller.
yeah, the fortune tellers are all women, right? You don't get very many men that read palms and do that kind of stuff. And mostly it's because you would never, if you were a person wanting to have your fortune told, you wouldn't go to a man. It's like, you don't know anything, I'm going to go to a woman. So they're all women. Anyway, so a type 1 error would be to decide that the fortune teller can predict when in fact they really are just guessing. What would a type 2 error be? That's part B.
That you concluded that she couldn't predict it, and then actually she could.
Yeah, from your study you conclude that she can't do it when in fact she can. That's a type 2 error. Okay? Let's see here. That one, because it's going to be just like the one we did. Let me go to the next page. Well, I guess they don't have one that I'm looking for. What I was trying to find was an example where the p-value was bigger than 0.05, so that your decision was to fail to reject. And then what kind of an error would that be if it was an error? That's a type 2 error, right? And he doesn't have any problems like that. But there's a lot of them where they say, describe what a type 1 error would be in the context of the problem. So let's look at this one, 950, detecting prostate cancer. It's referring back to a previous exercise, but it says a New York Times article from 1999 about the PSA blood test for detecting prostate cancer stated that the test fails to detect prostate cancer in 1 in 4 men who have the disease. For the PSA test, explain what a type 1 error is and explain the consequence to a man of this type of error. What would a type 1 error be?
False positive.
A false positive, which says what?
You might have to go into another type of test to figure this out. That could
Okay,
be
and
more
you're given the
dramatic.
consequence. But a false positive means the test comes back positive, but in fact they don't. So you reject the null hypothesis. Null is always none, right? So no cancer. So you're rejecting that. You say, hey, it looks like you have cancer. But then, so the consequences to a man who gets told he has cancer but he doesn't really, is he gets subjected to probably more invasive type of tests, more medical expenses, a lot of mental anguish, right? For the month or whatever it takes to get the results back of the better test, and then that test comes back negative. Oh, sorry, just kidding, you don't have cancer. Right? Now, what would a type 2 error be?
Fail to reject.
You failed to reject, and in fact, you should have. So the test came back negative. Remember, a type 2 error is a false negative. Test comes back negative, but they actually do have cancer. So what's the consequence to a man in that position? What'd you say, Marina?
Wouldn't do anything about it.
Wouldn't do anything about the cancer, so the consequence is you don't detect the cancer at an early stage, right? So you send them home and say, hey, you're fine. So they go on about life, and maybe a few years later, prostate cancer actually grows pretty slow. Now it's gone to a point where it's become very obvious that something is wrong, and they go back and they get tested again. This time they come up positive. So which is the more serious consequence?
False negative.
In this case, a false negative is worse than a false positive. Right? Now, what is this statement? To which type of error does this probability 1 in 4 refer?
False negative. Type 2.
That's a type 2 error. It says the test fails to detect prostate cancer in 1 in 4 men who have the disease. So you've got a 25% false negative rate with that PSA test. Which is why men who start doing regular PSA tests, if you're not having any symptoms or no reason to suspect that there be any cancer, then if it comes back negative, they don't do anything about it. But if the patient had gone to the physician complaining of something that could be because of it, then they don't trust this test very much. They'll do the PSA test, but even if it comes back negative, say, well, we probably ought to check a couple other things, maybe do the more invasive type test, right? So it has a very high false positive probability. Okay, the article also stated that if you receive a positive result, the probability that you do not actually have prostate cancer is 2/3. Explain the difference between this and the conditional probability of a type 1 error given that you do not actually have prostate cancer. Huh? It gets hard to read this stuff, doesn't it? So let's start that slow. The article stated that if you receive a positive result, the probability you do not actually have prostate cancer is 2/3. So this is what it says in symbols. The probability of no cancer given a positive test. Right? No cancer is the null hypothesis. So that's the probability that the null is true given the data I don't know how to write it other than to say positive test. It says, what's the difference between that statement and the conditional probability of a type 1 error? So what was a type 1 error?
Check that when it's true.
It's the other way around, right? Type 1 error, the conditioning type 1 error is the probability of positive test given no cancer. Right? You reject the null by getting the positive test, but in fact, there is no cancer. So that's a type 1 error. This is not a type 1 error. We don't have a name for that, but it is. This is a mistake, but it's hard to even discuss this as a probability because whether or not you have cancer isn't a random variable. Right? The randomness comes into play by drawing samples, right? So you can talk about the randomness of the results of your p hat. You can't talk about the randomness of whether the null is true or not. So that statement turns the conditioning around the other way. So that's the difference. Okay. And that, by the way, for those of you that are in some kind of a medical field, that is talking about the sensitivity of the test and the specificity of the test, which is reversing the direction of type 1, type 2 errors. Right? Okay, that's all the time we have. So that should get you through your homework. Tonight, by midnight, you have a 9.3 to do, so if you haven't done it yet, don't forget. Monday will be 9.4 homework. Okay? Then we've got one more section in Chapter 9 and the first section in Chapter 10 to do next week. And then we'll review on a week from today, we'll review for the test. We'll see you then.